Okay, let's go back to our power function. The power function, it should be n minus capital S squared divided by sigma star squared divided by sigma 0 squared greater than k squared n minus 1 alpha quantile. So this is the power 1 minus beta. And again, this thing is a random variable k squared n minus 1. So the power function can be represented as k squared n minus 1. This whole thing is a random variable falling k squared with degree freedom n minus 1 times sigma star squared sigma 0 squared greater than k squared degree freedom n minus 1 alpha upper alpha quantile. So this is the power function, is equals 1. It is denoted as 1 minus beta. So this is for right-sided one sample variance testing. So for left-sided testing, we just need to do minor modification. For power, so remember the PDF of chi-square distribution. This is PDF of chi-square distribution, and this is the shaded area is alpha. So this point on the horizontal line is denoted as k squared n minus 1 alpha. So if this shaded area is alpha, so this point on the horizontal line is denoted as k squared n minus 1 minus alpha. This is our convention for such notation. Okay, we have finished introducing the one-sided, one-sample variance testing. So let's take a look at the two-sided variance testing, one-sample variance testing. So it's just this: sigma equals sigma 0 squared, each alternative, sin squared, not equal to sigma 0 squared. This test statistic remains n minus 1 capital S squared divided by sigma 0 squared. So p-value is 2 times minimum of this probability n minus 1 small s squared divided by sigma 0 squared greater than k squared n minus 1. Probability n minus 1 small s squared divided by sigma 0 squared less than k squared n minus 1. So again, let me repeat. that this and this are both random variables following chi-square and -1 degree freedom. So this is p-value. And for decision rule, the decision rule is formulated as follows. So n-1 times left endpoint. Since it is a double-sided hypothesis testing, we need two constants: 0 squared less than chi-square and -1 is that equal to alpha L. Keep in mind this is random variable. And probability n-1 times cu, the right endpoint of the acceptance region is and we need alpha L plus alpha U equals alpha and remark in practice alpha L equals alpha U equals alpha over 2. This is our convention in practice. So for power in this case, is probability of n-1 capital S squared divided by sigma star squared. So this whole thing together follows so we need to specify sigma square equals sigma star square from the alternative parameter space. Then the power function is chi-square n-1 times sigma star square divided by sigma 0 square less than chi-square n-1 alpha L plus probability chi-square n-1 times sigma star square divided by sigma 0 square greater than chi-square n-1 alpha U So here, you need to be careful of the notation because we use upper quantile. So this should be 1 minus alpha U. Sorry, this is just alpha U. This should be 1 minus alpha L. Yeah, that's it. This is power for two-sided one-sample variance testing. So now let's take a look at two-sample variance testing. We have finished the one-sample variance testing. Let's go to two-sample variance testing. So for two-sample variance testing, we're interested in testing the following hypothesis. H now is sigma 1 squared equals sigma 2 squared. Okay, let's firstly do a quick review. Let me make a remark before we go into the two-sample variance testing. So my very important remark is that all of our testing works under such model assumption: normal model or non-normal model enlarged. So I will not repeat the model assumption for the following testing. So okay, let's do a quick review of today's material. So today we first talk about one-sided one-sample variance testing, and I said that the testing procedure is correct, and the normal model or non-normal model when n is large, which is supported by the central limit theorem. And for two-sided variance testing, also for normal model and non-normal model enlarged. Okay, let me write it down. And for two-sample variance testing, we also use the same model assumption: normal model or non-normal model enlarged. But here it is a two-sample case. So what is normal model in the two-sample case? So for two-sample, which means capital X1 to capital Xn1 following IID following n normal mu1 sigma 1 squared, capital Y1 to capital Yn2 IID normal mu2 sigma 2 squared. So this is called two-sample normal model. So we change this to non-normal model, two-sample non-normal model. We just eliminate this distributional assumption. So this is what normal model and non-normal model enlarged means. So for enlarged means, so non-normal model n1, n2, both large. So this is what two-sample mean. So let's go to detail of two-sample variance testing. So for two-sample variance testing, we utilize the following test statistic. The test statistic we use is capital S1 squared, the first sample variance of the first sample, and capital S2 squared is the sample variance of the second sample. And we know what? We know that n minus 1, n1 minus 1 S1 squared, sigma 1 squared, following chi-squared n minus 1, and n2 minus 1 S2 squared divided by sigma 2 squared, following chi-squared n2 minus 1. This n1 minus 1, this n2 minus 1. So let's substitute this result to the following to this ratio. this is sigma 1 s squared n minus 1 divided by n1 minus 1 n1 minus 1. So here chi squared n1 minus 1 is a random variable, keep in mind. And for the denominator, it's just sigma 2 squared chi squared n2 minus 1 divided by n2 minus 1. And enter h now, which is sigma 1 equals sigma 2 squared, which means sigma 1 squared divided by sigma 2 squared is just 1. Then s1 squared divided by s2 squared is chi squared n minus 1 n1 minus 1 divided by n1 minus 1 square n2 minus 1 divided by n2 minus 1. And we call such test statistic is f test statistic, and it following f distribution with degree freedom 2 degree freedoms. The first degree freedom is n1 minus 1. The second degree freedom is n2 minus 1. So f distribution is a famous distribution. You can check table, f table. So let's see the p-value for such testing problem. The p-value is 2 times minimum of p-value f random variable. So this again means a random variable greater than smaller s1 squared divided by smaller s2 squared. The probability of kept the random variable following f distribution with degree from n1 minus 1 n2 minus 1 n1 minus 1 n2 minus 1 less than small s1 squared divided by s2 squared. This is the p-value in this case. And for decision rule, is probability of left endpoint less than this random variable following f distribution n1 minus 1 n2 minus 1 degree freedoms equals alpha L. The probability of FCU greater than fn1 minus 1 and 2 minus 1 alpha u, and we need alpha L plus alpha u equals alpha, and in practice we often set alpha u equals alpha L equals alpha over 2. And the last part is power. So for power, this is, we need to specify sigma squared divided by sigma 2 squared, not 1, because sigma 1 squared and sigma 2 squared are from the alternative probability hypothesis. And we specify sigma 1 squared divided by sigma 2 squared equals theta. And then for the capital S1 squared divided by S2 squared is no longer F. We need to divide it 1 over theta, and then times theta, then it becomes, so this part becomes F, becomes a random variable following F distribution. greater than and 1 minus 1 and 2 minus 1 alpha u plus probability. Again, here is the random variable f and minus 1 and 2 minus 1 times theta, right? Less than f and 1 minus 1 and 2 minus 1 1 over alpha L. So this is the power for two sample variance testing. At this stage, we have finished the variance testing part. This is the first topic of today's lecture. Let's do a quick review. Into this lecture, our first topic is variance testing. It divides two types, one sample and two sample. For one sample, for normal model and non-normal model enlarged, we kept the S-squared. Sample variance is utilized in variance testing. And H null, we use this test statistic n minus 1 S-squared divided by sigma 0 squared, following K-squared with degree from n minus 1. So to compute p-value in such way, for single-sided testing, decision rule and power. For double-sided one-sample testing, p-value is 2 times the minimum of these two probabilities, and decision rule is constructed from the following formulas. And for power, it is a summation of two probabilities. For two sample variance testing, for normal model and non-normal model enlarged. So for two sample, we have two samples, each following normal and non-normal model, n1 and 2 both large. We use this test statistic, another new knowledge. The ratio of sample variances and the H null. We introduced to you that and H null, this test statistic is called F test statistic, and it follows F distribution with degree freedoms n1 minus 1 and 2 minus 1. And for this testing problem, the p-value is 2 times the minimum of these two probabilities. A decision rule can be constructed from the following formulas, and for power, it is the summation of two probabilities. Okay, we have finished our first topic of today's lecture, variance testing.